like to use this opportunity to give a short historical introduction to this presentation, because it concerns my own activity, and the story started 20 years ago. So 20 years ago, in 2005, people did not believe in Bose-Einstein condensation of exciton polarities, especially at elevated temperatures. And there was a big challenge to convince the community that it is indeed possible. So theoretically, we published some papers already, even the book where we declared that in finite size two-dimensional systems, this bosonic condensation must be possible, but none of experimental papers was accepted to any high-level journal. We collaborated with Lesidang group from Grenoble, and despite all our efforts, the paper was rejected systematically from everywhere, and it ended up in Physical Review B in 2005, and the editor even imposed in the title, a change in the title. We had Bose-Einstein condensation of exciton polaritons in microcavities in the title, and the editor, when the paper was accepted, insisted that we put non-equilibrium Bose-Einstein condensation. Okay, then the challenge was to propose a criteria for this effect. What should be observed to enable one to claim that really this is Bose-Einstein condensation? And the logic was this one, that Bose-Einstein condensation is a phase transition. Any phase transition should be characterized by the appearance of some order parameter. So what is this order parameter for polariton Bose-Einstein condensation? Something that is zero below condensation temperature emerges, or above condensation temperature and emerges below condensation temperature. So I thought that polaritons, they have polarization. And nothing in the system theoretically defines this polarization. But once the condensate is formed, it must be a coherent state with some specific polarization. It cannot have zero polarization. It must be fully polarized. If it is an ideal Bose-Einstein condensate, so fully coherent state, it must have 100% polarization. So I started to talk to experimentalists and ask them to check the polarization as a function of Planck power as they go through this threshold of polariton Bose-Einstein condensation. And one who measured it was Benoit Devaux in Lausanne in EPFL. So he measured, and indeed, he observed that below threshold the polarization is zero or nearly zero, and above threshold there is a very strong polarization. But it was not convincing for him, because he said, well, this is linear polarization that is pinned to one of the critical axes. So it is not spontaneous symmetry breaking, it is something that is imposed by the symmetry of the structure. There is no, it is no, so he put this result in the paper, but as some supplementary evidence, but he did not believe that this is really the order parameter for Bose-Einstein condensation. And that was a challenge to us. So why, in principle, the polarization should be random. Any polarization must be possible, circular, elliptical, linear, anyhow oriented. It just needs to build up from 0 to 100%, theoretically, in the ideal model. But experimentally, it was not so. So at that stage, there was eventually a postdoc in my group in France and in UK later, and Eurobo, who was visiting from Mexico for 1 year. So we started thinking about that problem, and Jura, I think he was the first to develop the model of anisotropic polariton interactions. His argument was that the polarization indeed is not fully random, it is linear, because the linear polarization minimizes the interaction energy of exciton polaritons. Basically, if all polaritons have parallel spins, then they repel each other stronger than if half of them has spin up and half of them has spin down, which corresponds roughly to the linear polarization. So linear polarization minimizes the interaction energy. Okay? Because polaritons with parallel spins repel each other, and polaritons with anti-parallel spins, they quickly interact. And this resulted in a theoretical paper that we published, I think, in 2006 with Yura and Ivan and PRL, where we described the polarization state of the polariton condensate. We said that it should be linearly polarized, and moreover, we solved Bogoliubov-Dejean equations to obtain the branches of excited states of this condensate. So there are two branches of excited states polarized parallel and orthogonal to the condensate. They are characterized by slightly different sound velocities. That was all published. And at that stage, I think, it was published in PRL, by the way. At that stage, I moved from France to UK. And when I moved from France to UK, which was in May 2005, I had some startup funding to have one postdoc and to have a visiting scientist, visiting professor for a year. So postdoc was Ivan, who moved for 2 years, I think, to Southampton. And Yura came for 1 year as a visiting professor. And as everyone come together in Southampton, we decided that we'll do the same in the magnetic field, which is typical, in theoretical physics. You have done something, then you do the same in the magnetic field, and you make one more publication. So when we did the same in the magnetic field, which is not a big deal, as a side product, it emerged that the chemical potential of polariton condensate has a non-trivial behavior as a function of magnetic field. Namely, for the field from 0 up to some critical field, it is independent of the field. And then it goes linearly down with the field, reflecting Zeeman splitting. So without the polariton condensate, you would have linear dependence, which is just Zeeman effect. But with polariton condensate, due to the anisotropic spin-dependent polariton interactions, there is this non-trivial dependence. And we published it in a small journal, Physics Letters A, I think also in 2006. And Ivan was very good in inventing new terms, new terminology. He said, let us call it Spin-Meissner effect. Why Spin-Meissner effect? Because usual Meissner effect in superconductors means some screening of external magnetic field, full diamagnetism. So magnetic field does not penetrate into a superconductor. Here, well, it does penetrate, but still Zeeman splitting, that is a signature of magnetic field effect, is exactly 0, is fully suppressed up to some critical magnetic field. Yura, who was always conservative regarding new terms, he was reluctant to put it in the paper, and we did not put it in the paper. But I put it then in the second edition of or the third edition of the microcavities book, where these very fresh results were included, and they're still there, even extended for a finite temperature case. So I think the term Spin-Meissner effect, it first appeared not in the original paper, but in the book. That was published soon after. And interestingly, this effect, it was very soon experimentally confirmed, or partly confirmed, by Vladimir Kulakovsky here in Chernogolovka, who observed it on samples from Sven-Höfling, and there was a very nice PRL paper. So indeed, they saw some quenching of Zeeman splitting, but then more complex polarization behavior, not exactly as we predicted. So then there was some development of theory, discussion, etc. And interestingly, then in first papers, I think also Kulakovsky did not call it Spin-Meissner. But somehow this term came to the community, and already in the paper where I took part with the Polish group from Barbara Kietka, they put it in the title, I think. So they observed this effect, very strong actually in diluted magnetic microcavities, and then I think it was observed in a variety of systems. So I don't know if the effect is very useful, but at least it has its own name and it was experimentally confirmed. So I was very pleased to know to learn that Andrey paid attention to these old works and somehow he extended the theory to the system of coupled polariton condensates. So let us listen for the next story about Spin-Meissner effect.
Thank you for this huge, brilliant introduction. Just remark to the audience, I did not pay to our head of the department for this nice job, because it really will help me to present my ideas. Okay, so we can start with the second slide. The work was done with my collaborators, with Igor Chesnov, with Anton Nalitov, and Ivan Shiliv. So, going to the presentation plan, we already continue the part of the introduction presented by Alexei. After that, I will show you the classical model, the classical Hamiltonian, which we will use which we used already for our calculations, some approximations, and results for already known result for single condensate, and for the different geometries where condensates, or we can call it as nodes, are arranged in in some lattices, like just polaritonic dyad, triangle, and square of coupled condensates. And in the end, I will draw the conclusion. Okay. So again, motivation. Why the study of lattice systems is important? Because we know many interesting phenomena connected with the lattice. One of them, it is a ferromagnetism. And on the one hand, if we want to analyze it on the basis of experiment, it's really difficult. Why? Because, of course, it should be done. But in order to check some theoretical predictions, which are constructed usually on the basis of some ideal models, it's difficult to check it or to check some fundamental mechanism experimentally, due to the constant presence of, always present of what? Of impurities, defects, and different unpredictable factors. On the other hand, we can address to what? To numerical simulations, yes? But we all know that with the growth of the system, the complexity of calculations also dramatically increases. And at this stage, like recently, appeared some idea regarding the simulators, like physical simulators of some of behavior of some ideal models. Yes, one of these platform, it is well known, called atoms in optical lattices. When we take lasers, achieve interference between these lasers, and also cool the atoms up to the nanokelvins in order to achieve the de Broglie wavelength should be already more or less the size of the distance between atoms, yes. And we can already model some and check some ideas, some theoretical fundamental mechanisms on these ideal lattices without impurities, without defects, and so on. But there is some disadvantage. It's important disadvantage connected with the low temperatures. Another platform, it is based on the polaritonic condensates of polaritons. There are some advantages. First of all, it is high temperatures up to the room one. So, moreover, we can achieve due to the strong, due to the exciton interaction, we can achieve high non-linearities in this system. And also due to the fact that polariton also consists of exciton, we have a spin degree of freedom, yes, because exciton, it is a mixture of two charged particles with spin 1/2, and of course, exciton has its own G factor and so on. And this degree of freedom can also be exploited for modeling some physical systems and to check the behavior of some models. Okay. And of course, we should analyze the huge amount of effects in these systems. And one of these effects, it is so-called, as was already presented by Professor Kavokin, Spin-Meissner effect. Yes, as it was already said, it was called in this way due to the analogy with the full screening of magnetic field in superconductors. So here also cited the work by Natalia Berlova and others, where they demonstrated how the classical XY Hamiltonian, just ferromagnetic system, can be modeled by based on the polaritonic platform, how it can be behavior can be demonstrated by means of the specially arranged condensates of polaritons, and they demonstrated that the ground state of these physically different systems, if we correctly choose the observables, then these ground states are the same. Okay. Within my presentation, I would like to show you two really important slides regarding the mechanisms. It is the first slide. Again, in polariton condensates, we have Zeeman splitting connected with the fact, as I already told, that polariton partly consists of exciton. Also, in planar resonators, there is also always is presented TETM splitting. It is caused by the difference in dispersion relations and energy dependence of different electromagnetic modes, and this splitting leads to the appearing of some effective spin-orbit coupling in our system. Or we can say, in other words, that it just leads to the appearing of additional effective magnetic in-plane magnetic field, which affects on the pseudo-spin of condensates. The next important thing, it is a spin-anisotropic polariton-polariton interaction. Again, due to the exchange mechanism of interaction between excitons. Spin-Meissner effect, where we should analyze the interplay between this spin-anisotropic polariton interaction and Zeeman energy. And the last maybe point, that this Spin-Meissner effect are affected by the special geometries. In other words, we can say that if our condensate are put in a specially prepared external stationary potential, yes, it can just break down the pure Spin-Meissner effect behavior. And the next slide, I decided to edit after my discussion with head of our center, with Professor Kavokin, where he suggested to rethink or to think in another way about mechanism of what is going on in the system. And like step by step, thesis by thesis, I would like to present it within my presentation, yes, within my talk. And first, just before we continue already with some specific model approximations and results, we should discuss. We have a condensate, single condensate. We can consider it as a single condensate or a net of nodes or condensates. Okay, it is a question of interpretation. Let us consider it as a single condensate, which is can be spatially localized or distributed by means of some potential. Of course, we come to the localized regions for this condensate. Next, due to this localization in the expansion for wave function, we should have components possessing non-zero momentum, non-zero wave vectors, and it allows to manifest itself TE-TM splitting. Yes, and of course we should take into account this splitting in our model, this difference of energy for different modes. So next, as I already said, due to the appearance of additional in-plane magnetic field, some effective in-plane magnetic field, we face with some combination of real magnetic field perpendicular to, but okay, we can do some additional seminar, but I do not want to hurry up regarding my presentation. Okay, we will just finish on the stage, which will be. Due to this combination of real magnetic field perpendicular to the plane and effective in-plane magnetic field, it leads to the appearing of some topological phases. Okay, we will see that we found some vortex, half vortex, hidden vortices states, and so on. Yes, and this complex spin texture depends on the geometry of external potential, we can say. And it's important that due to this fact, already magnetic field enters, this effective magnetic field enters the kinetic energy. But in terms of our model, our discretized model, the kinetic energy, it's common for discretized model, and enters the Hamiltonian as just hoppings. Yes, it's just hopping between nodes, and we have here two types of hopping: spin conserving and spin flipping. And due to all of these factors, we come to the fact that Spin-Meissner effect can be broken down for some special arrangement of our condensates. Like we come to the diamagnetic shift, with respect to the external magnetic field for chemical potential. Chemical potential, it is our main observable because it is just the energy of photoluminescence. Yes? Okay. So, okay, I already discussed goal and main findings. Yes, we just analyzed already a well-known effect for specially prepared, specially arranged condensates, so specially prepared external potential to which we put our condensate. It is the model, it is Hamiltonian in terms of creation and annihilation polariton operators labeled by A. First term, it is just a standard Zeeman term. Next, it is polariton interaction within one node. Yes, also with the same spin. And two terms which can be interpreted as poppings or as kinetic energy terms. For discretized model, it is the same. On the second line, first term, it is just interaction between nodes when one polariton jump to another node with spin conservation. And another term, like proportional to delta J, is associated with already spin flip interaction between nodes. And this, also you can see here exponent power I theta Lj. It reflects what? It reflects the dependence of the tunneling of polariton. It can have a linear polarization perpendicular or along the direction of tunneling. And this theta Lj, it is just a double geometrical angle between condensates. Why double? Because if we try to remember that linear polarization can be expanded in terms of circular polarization with factors like exponent minus I alpha, where alpha is just a geometrical angle, and exponent plus I alpha. Yes, if we change our geometrical angle by something, it leads to the difference between circular polarization, double dependence on this change. Yes, and therefore we have this type of exponent because all of these are presented in terms of in the basis of circular polarization. Yes, next from this secondary quantized Hamiltonian, we assume that we have enough huge values of pump. Yes, intensity is large, and we as like more or less a standard step within the quantum optics, we use the combination of coherent states. Psi is just a tensor product of these coherent states, which is characterized by the level of occupancy n and also by the phase. Each node is characterized by n and by phase. And global coherence can be established as it obviously via couplings J and delta J. Okay. Also, it's useful for characterization of the system to introduce the component of pseudospin as J and as Z, as X, and as Y, but within our work, it was enough just to use as Z. Okay, go next. If we take the Hamiltonian and address to the presented on the previous slide state, we can already rewrite our Hamiltonian as a classical one. which depends on the parameters of the system, of course, and variables. It is a phases. Phi j plus and j minus correspond to the spin up and spin down, or polarization, right-hand side polarization, left-hand side polarization of polariton within one condensate. And SJZ just characterizes the degree of circular polarization of some specific node. Okay. And main observable, of course, for us, it is just a chemical potential because it can be measured within the Y experiment. And here you see a purely thermodynamic definition of this quantity. Yes, it is just a partial derivative with respect to the number of total number of particles. It is just an energy which will appear if we put to the system some additional particle. Okay.
One important assumption was made in this slide that all condensates are equally populated.
Equally, yes. Thank you for this remark. Yes, they are equal. Total occupancy are equal, but n plus. Okay, we have for each condensate n plus, plus, and minus equals to n, and this n is constant. Yes, we assume that by experiment it is possible to achieve this condition. Okay, it's questionable, but we assume theoreticians. Okay. And as already told and declared by Alexey, for a single condensate, the results are known, and for chemical potential up to some critical temperature. I mean, for single condensate, it means that H1 and H2 terms vanish. Yes, we have only H0, and it's just not a difficult problem just to minimize H0 when we have only one node. And this minimization leads to this result when that in the spectrum there is no gap up to the some critical magnetic field, and after this critical value of magnetic field, when condensate is already fully polarized and spin-anisotropic interaction cannot more compensate the energy connected with the Zeeman term, yes, we should already face that in the spectrum should appear some gap, or just like Zeeman splitting.
This is mean field approximation.
Yes, mean field, classical.
And you don't consider
no, just huge intensities, huge pump, and like
even near the TC.
It's just zero.
Yeah,
we are in
okay, near effectively the point where transition occurs.
connected on the magnetic field. We are always on the at t equals to 0.
Not TC, but the point where second order phase transition occurs. In terms of magnetic field, usually the fluctuations are important.
You considered based on the chemical potential is continuous, therefore you say that okay, it is a second order phase transition, and I try to.
Yes, it can be actually. This is an interesting question. It can be derived in one line that Spin-Meissner effect. So the energy that Andrey introduced, it is some kinetic energy, Zeeman term that is like factor SZ, the polarization of polaritons along the magnetic field, and there is some interaction term that is proportional to SZ squared. So SZ it cannot grow more. So it depends on the magnetic field, and exactly at this critical magnetic field, it saturates. It achieves. So all polaritons are polarized. The critical magnetic field you find minimizing this expression over Sz. Yes, so just this condition dH over dSz equal to 0 gives you the critical magnetic field. Now, chemical potential, why it is 0? Because chemical potential is dH over the number of particles, but there is no number of particles in this expression until you achieve Bc. Yes, so only if B is more than Bc, some dependence on the number of particles appears. But before that, the chemical potential is just fixed, 0. So for B less than Bc. Now, what happens exactly at Bc? That's a good question. But in principle, at 0 temperature, it's just the point where all everyone is fully polarized.
I see your point. You mean that the system, as if we follow the second order phase transition, we know that fluctuations are crucial,
Yes,
and
so
systems are so soft.
The changes from 0 to something. So
I see. But my answer here just a mean field, okay? Like
Yeah.
lambda of 0, and I cannot say something more regarding fluctuations. Of course, if we recall critical phenomena theory, we know that fluctuations crucially change the critical behavior.
Near the where
the system
becomes zero.
the system. Okay, it's a good question regarding the fluctuations, but here, okay, we just stop on the mean field approximation.
I think you are mostly interested in the region where B is much less than Bc, where the Spin-Meissner effect is strong. And everything, the interesting thing comes from here. Because what Andrey told is that if there is a topological phase, then this term becomes dependent on the magnetic field, and then something changes in this reasoning.
Mm-hmm. Okay, yes, thank you. Can I ask? Sorry. Okay. Okay. So for single condensate and also the list of papers connected with this effect, you can see. So go next. Now let us consider already two coupled condensates. Yes. And start with a simple consideration. If we don't have and we don't take into account the spin flip term, we will see that Spin-Meissner effect is still there. Yes, it will be it is not broken. Only we start to slightly turn on spin flip. Yes, we allow for polaritons to jump from one condensate or from one node to another node with changing of spin. We can see that it leads to the appearing of some diamagnetic shift. And for small delta J, okay, it is a good question regarding the real values of this hopping. From the experimental point of view, but at least on the paper, we see that for some values more or less not so small, it is quite visible. And from the pure independence and after that linear dependence of chemical potential on magnetic field, we obtain some diamagnetic behavior at the small magnetic field, and at the end, it, of course, come again to the linear behavior. Okay. So we obtain this kind of approximation. for that. And also we should add some comment that due to the presence of delta J of spin flip terms, it locks the orientation of polarizations. Depending on the sign, we demonstrated it, depending on the sign of delta J, it locks polarization perpendicular to the line connected the nodes, or a line or along to this line connected with this diode. It is some new interesting effect connected with the polarization locking, which we also observed apart from the observation of Spin-Meissner effect broken down.
So is it a bistability effect? So both solutions have the same chemical potential?
I mean, okay, again, depending on the sign. Yes, it is a good question which sign we really have in experiment, I mean, regarding delta J. But if we analyze arrangement of polarization, which can be expressed as just a relative phase over 2, yes, we see that ground state, and we are analyzing only ground state, correspond to the locking of polarization. It's just interesting effect. Without it, without delta J term, polarization can be oriented freely.
I think the locking of polarization was actually experimentally shown in 2 coupled microcavities in Jacqueline blocks.
Okay.
In case we're not citing, just
okay, yes, see, but we have opportunity to cite it. But okay, yes, we also obtain polarization locking. So, and here, as I already demonstrated you this slide, we shown behavior of degree of circular polarization as Z component of pseudospin, and the behavior of chemical potential for different delta J. You see that for delta J equals to 0, Spin-Meissner effect is restored. Okay. Go next. Already more complex geometry. It is just a condensates which are arranged in a triangle, yes? Equilateral triangle. In our consideration, we separate. What? One case, it is a case of so-called ferromagnetic system, where J is negative. And it is just a terminology taken from the ferromagnetic systems, yes, from magnets. And for J positive, we have antiferromagnet case. These two cases should be considered separately, because as we know already from the analysis of just conventional ferromagnets, it is qualitatively different cases, because in one case we have some frustrations, because for antiferromagnetic it's difficult to choose how if you want to be oriented in opposite direction, some, I don't know, two neighbors want just aim to be oriented in opposite direction, but the third neighbor does not know how to be oriented, to be oriented and to have opposite direction with this neighbor or with this, and energetically profitable to have some frustrations and to have arrangement of spins with 2 pi over 3. Yes, therefore it's not a like surprise for us that here we also should have some differences in consideration when we analyze triangle. Okay, but fortunately for us, for our work, it was maybe a surprise or not, antiferromagnetic case is more or less trivial, on the whole space of parameters, it has only one phase, one type of arrangement. But more interesting case, it is a ferromagnetic case where J is negative. And here we've observed different phases. When we just pronounce this word, I mean phase, it means that the phases of condensates have different symmetry and they have a different arrangement. And what we've observed, we observed asymmetric phase, the phase which is characterized by half vortex states, and hidden vortex states. I will show you on the next slide.
So when you mention negative diamagnetic shift, it sounds awkward. Right? So what is a negative diamagnetic shift? Diamagnetic shift is always positive.
I mean, okay, like it is just a sign of okay, maybe it sounds bad. We are talking just about sign of derivative of chemical potential. It goes down or up, because in our consideration we've observed interesting thing that chemical potential can even grow.
Yes, with magnetic field.
Okay. Yes, with magnetic field. Yes. Okay. It is one of the main figure in our paper regarding the triangle.
Yes, but let me emphasize that here there is no orbital effect of magnetic field. Magnetic field only creates Zeeman splitting. Still, there is this kind of behavior because of the interplay between three factors, the topological phase, let's say TTM splitting, spin-dependent polariton interactions, and Zeeman split.
Yes, right. But also, it's important that on a square, where we will see, maybe we will not see, but okay, in square, the Spin-Meissner effect is restored for some non-trivial region of parameters. By non-trivial, I mean non-zero value of delta J and non-zero magnetic field. And it is restored. And it is restored only due to the fact that not only delta J term, but also J term in the Hamiltonian. It's like so difficult play between all of these contributions. But yes, we can highlight spin-anisotropic interaction, Zeeman, and TE-TM splitting. So look at this, please, phase diagram. We highlighted here three phases. Phase number one probably possesses the most interesting features connected that even degree of circular polarization for nodes are different. Two of them always have the same, and one has different one degree of circular polarization. It's our some observation. Moreover, I just waited for a question regarding what does it mean, like red arrows and green arrows. Red arrows are just a total phase. It is just a sum of phi j plus and phi j minus over 2. And green line, it is just the main axis of ellipse connected with the polarization of this node. It is just relative phase of the condensate over 2. Yes, and how this ellipse is close to the lines or to the circle, it reflects how this node is polarized, circularly polarized.
Is it an illusion that these ellipses have different sizes?
It's not illusion. It's a feature, Anton. It's our feature that in this phase, two of them always have a different degree of circle polarization in this phase. Probably it is most achievable phase within experiment because it is just near to zero in terms of magnetic field and in terms of spin flip hopping, spin flip coupling. Yes.
So the size of the ellipse gives you the degree of linear polarization.
Yes. Okay, it means that, of course, if we come to the borders, aspect ratio between axes of ellipse should be changed, but it is just schematic demonstration for some points on this phase diagram.
Probably not the best one because it's not obvious from the illustrations.
There are many things which are not obvious, but I try to do my best to present it. Okay, the second phase is characterized by so-called already known half vortex structure, where one subsystem, the component with one polarization, say with positive, with like right-hand side polarization, they are all nodes are homogeneous, oriented in the same direction. I mean phi j plus, for example. But another subsystem, phases of components which have different polarization, they have some vortex, yes, some winding and just a changing of phase by 2 pi over 3 when we go from one node to another and so on, yes. And therefore we see here this kind of arrangement for total phase. And hidden vortex arrangement, it's not obvious because here we see demonstration of total phase, but we've analyzed it and it's just a hidden vortex because both subsystems, both polarizations, both components on a node has a vortex structure. Both polarization has a vortex, but this vortex in an opposite direction, and therefore in total, for total phase, we don't see any vortexes. Okay, and left-hand side and right-hand side correspond to the delta J plus and delta J minus, but qualitatively they are more or less the same, just the polarizations are locked along the bisectors or perpendicular to them. Okay.
Is the fact that there are three phases related to the three sides?
No. Okay. Phases. Okay. Again.
You have three phases.
Yes. It depends on the.
This is for system with three sides.
Yes.
For a square, four phases.
How many phases per square?
Okay. Three also. Okay.
How did you get this phase diagram? Is it numerical?
Yes, numerically and semi-analytically.
And how to get boundary between phases?
Okay, here
How to draw it?
it can be done not in all cases, but it can be done numerically and also analytically. We should compare just different spin configuration. We find we find phase configurations. Yes.
Energy.
Put it to the energy and compare when one phase begins more energetically favorable than another one, like some border, and we can find this condition. Yes.
Yeah.
But again, is it an illusion that there are four different colors?
Yes, it's not illusion. This is true. It is some requirement from one of our co-author because we did not want to introduce some additional phase like phase one and phase one prime. You see these colors, different colors, blue and deep blue. it corresponds to what? It corresponds to the sign of derivative of chemical potential with respect to magnetic field at the initial stage. You see? It means that
Its initial station would.
I mean regarding with respect to magnetic field. I will show you. Now look at this. Let's try to go from this point through the straight line and we should start to increase magnetic field. I mean, we consider these lines from phase 1 to phase 2, these lines. Because I don't have just time, I try to explain it qualitatively. And look at the behavior of chemical potential. These lines, again, we fix the value of delta J, as here, and go through this line. We just increase the magnetic field from phase number 1 to phase number 2. This line, again, corresponds to delta J equals to 0. We see, of course, it's not a surprise, the Spin-Meissner is restored. And we start to increase the value of delta J. You see, we have a quadratic, near to quadratic behavior with respect to magnetic field. But for light blue region, it is positive. It has positive coefficient. But for small, really small region, it has negative coefficient. But in all of this phase, of course, Spin-Meissner is broken down. It's one of the conclusions. Next, going to the second line, to the second phase, we obtain more or less linear behavior with some Laurent-like corrections, like 1 over magnetic field. We obtained it analytically, but I don't just have time to present it.
Maybe we can try to understand qualitatively what you show, because there is a lot of zoology here, but physics is maybe not so difficult. So one thing that was shown in 2009 by Andrey and Kudlis was that if you have Aronoff-Bohm interferometer, so a circle like that, and you have Zeeman effect, so magnetic field that leads to some spin polarization, and TM splitting. TM splitting, this is the dependence of kinetic energy on polarization. TM, T, these are orientations of polarization vector with respect to the wave vector. So if both of these are present, both of these are non-zero, then there is a topological phase emerging, some kind of Berry phase. And when it emerges, it means that it is not equivalent if you go clockwise or anti-clockwise around the circle. So this is like in Aronoff-Bohm effect, but there is no direct orbital effect of magnetic field. But there is some kind of effective orbital effect of magnetic field through this topological phase that is dependent on magnetic field, through the Zeeman term. And of course, it affects the kinetic energy. So when we write this chemical potential and obtain that it is 0 up to here, we assume that we put 0 point on the energy axis at some specific point that corresponds to the kinetic energy, to some specific kinetic energy. This is where we put 0. But it turns out that this kinetic energy in this regime, it depends on the magnetic field, and this gives us this so-called diamagnetic, effective diamagnetic shift, right?
Yes, but okay, I'm not sure about interpretation it can be, but effect, yes, like this.
So now when Andrey considers three nodes, why three? Because three already gives you the Aronoff-Bohm configurations. Unlike two, I think for two it is more tricky to understand. But three, you have this circuit. So you can go clockwise, you can go anti-clockwise, and the phase that you gain in the regime of non-zero topological phase would be different. And this is where the effect comes from. So you need at least three. You can have 4, 5.
Any
whatever.
configuration which we can put on a circle.
Yes,
Yes.
any configuration that you can describe by a circle.
By circle.
And then all the zoology comes then from the specific arrangements of phases between these nodes. I think if you take 99 nodes, you will have also many more phases. But does it make sense to take more? I don't know. Qualitatively, the effect comes from the fact that you have both TETM splitting and Zeeman effect. And TETM splitting you have because you have spatial inhomogeneity of the potential. In the spatial homogeneous potential, you only have condensate at k equal to 0 point. Yes, a plane wave, and there is no TETM splitting. So this effect would vanish. But Andrey, what he does, he confines his condensate in nodes. So localized wave functions, they have non-zero k. And then that is why this non-zero TETM splittings, they start playing a role.
Manifest themselves. Okay, thank you. And yes, like it is a behavior of chemical potential. We also see some abrupt behavior of chemical potential. It is just not, it doesn't have a, as we checked, so large slope ratio. It is really just a jump from one phase to another phase. It's also one more interesting observation. So, and on the right panel, you see for different values of couplings, the sign of derivative of chemical potential with respect to magnetic field. And you see the small region, like where these lines, this quadratic behavior on magnetic field goes down, not like as usual, but not goes up. This figure corresponds just only to the points from the red region. Okay. Regarding square. Okay, I would like to just to show you.
Is it that important? Because you can have 3, 4, 5, 6.
It's important because here we obtain restoration of Spin-Meissner, because behavior of chemical potential here is really not like in a triangle. It's more like in just a single condensate. Look at the phase diagram. There are also three phases. And in contrast to the triangle, ferromagnetic, so-called ferromagnetic and antiferromagnetic cases are the same. I mean, more the same. I mean, in both cases have three phases, and yes, due to the lack of frustration which we have in triangle.
So any even number of nodes would be good, yes, because it does not allow frustration of antiferromagnetic.
As we believe, yes.
But every odd number is more tricky because
yes.
The absence, dependence of frustration and the number of the nodes on a circle, it was shown by Lagudakis group some time ago. So indeed, it depends on the parity of the number.
The main conclusion after my talk that everything already was done by Lagudakis. Okay, experimentally.
It's just the frustration.
I see. Okay, I see. Okay.
But he didn't use magnetic field follows. I think there is no Spin-Meissner effect in his world. It's just
Yes.
But we did not find any connected with like the presence of magnetic field.
But frustration is present even in the absence of magnetic field.
Okay, yes, okay, I believe, I know. But I mean, okay, it's see like at zero magnetic field we have already two phases, of course. So the first phase is characterized by homogeneous ordering both total phases and polarization. They can be oriented in any direction, but they should orient it simultaneously in one direction. But direction is arbitrary one. And it's interesting that in this you see highlighted by white lines. In this region, even for non-zero spin flip, for non-zero magnetic field, we see that Spin-Meissner effect is presented. Because it's interesting fact that in square, it can be really easily understood. In square, neighbors are located to each other, which angle? Like it's p over 2, yes? But in effective Hamiltonian, if you remember, with the spin flip hopping, we have exponent power I theta Lj, where theta is just a double geometrical angle. And if we use this geometrical angle as p over 2, this exponent gives just plus minus 1. It means that effectively for H2 term in Hamiltonian, effect, they just compensate neighbors compensate effect of on the energy, compensate each other. One term gives plus 1, one term gives minus 1, and they just destroy each other. And therefore, just effectively, this kind of arrangement at all does not feel any term connected with spin flip. Of course, still some critical value where where the hopping, with the coupling with spin flip is less than just ordinary hopping with the spin conserving.
In terms of lattice physics, one can think of this square as a plaquette, and one plaquette acts the same as a single condensate. So Spin-Meissner effect is restored.
Yeah, okay, yes. And in this blue region without white lines, we will observe just a linear dependence as for a single condensate, linear dependence on chemical potential. Next, also interesting phase number 3. There is no Spin-Meissner effect, but we should highlight this phase because of interesting of arrangement of polarizations. Due to some mixture of windings of phases of subsystems, I mean polarization components with circular right-hand side circular polarized light and left-hand side circular polarization. Yes, the combination of different windings leads to the so interesting behavior of polarizations. Polarizations in this phase are also locked, but they locked in a special manner. Omega does not depend on values of couplings, but omega should be the same as it's shown on the figure for all nodes. I mean, omega with respect to this line, omega with respect to the negative or x axis, and so on. But omega can be different, arbitrary. But polarizations are fixed. They can just change like this. It's also interesting, in fact.
You do not have much time.
But Alexei, you taken.
I have taken 15 minutes of your time.
And it means that I still have 5 minutes. Yes, thank you. And but because it's more or less last slides, everything after that is just mathematics. And interesting phase where we have some competition between two types of couplings. It is red region, phase number 2, where we have just some arrangement of two dyads. You see, we have one dyad and another dyad, and we have some distortion of their common orientation, how they are oriented with respect to each other. And okay, we've observed that it is energetically favorable for condensates to have this type of arrangement for polarization. And already look at the most probably interesting the figure with the dependence on chemical potential. You see what? You see we start from one point here, for example, from 1.2 for delta J, and start to increase the value of magnetic field. It means that we are in a phase number 3, phase number 2, and next in phase number 1. Because observation of behavior of chemical potential on these lines is not interesting. It's just trivial. It is the same for all these cross sections. Okay, and if we look at this, you see, we at the beginning we are on phase number 3. We see again some diamagnetic shift. Yes, quadratic behavior of a chemical potential on magnetic field. Next, Spin-Meissner is restored. We see the absence of sensitivity to the magnetic field. And when we achieve the state when condensates are fully circularly polarized, again, yes, Spin-Meissner, not Spin-Meissner, I mean like that Zeeman term cannot be already compensated by a spin-anisotropic interaction. And we obtain again linear behavior of chemical potential, just the Zeeman split. Yes, probably it is one of the most interesting results of our paper, of our work, that in some interesting region of parameters here, Spin-Meissner can be restored, not only here. So probably, okay, last slide and conclusions, that we analyzed from the other side, from the other angle, we decided to look at the already well-known, well-established Spin-Meissner effect, which was demonstrated for single condensates, both experimentally and previously theoretically. And decided just to arrange our condensate to put it in a specially set stationary potential, non-homogeneous external potential, and look at the effect that we obtain some topological phases and how these topological phases affect on the Spin-Meissner effect. It can be restored, but in common, it is broken down. That's all.
Thank you very much.
I think that,
What was it?
finally, what do you offer for experimenters? So what do they measure and what do you suggest? Well, they have, let's say, triangle, of condensate. What do they measure? Polarization of
and photoluminescence in the presence of magnetic field.
Okay, and they should changing or varying magnetic field.
I think as they should
see variation of phases for given lattice.
and I think also they should change distance between
but distance,
condensates.
maybe it's not so easy to change, but magnetic field.
I mean, distance should affect on the couplings.
I understand.
Yes, and they should just change the magnetic field and the distances between condensates.
So, and other such experiments?
I don't know. We did not find this kind of experiments. I sent it to Pavlos, maybe.
Oh, Pavlos doesn't work in magnetic field.
He's planning to. They are installing magnetic wires.
Maybe he will be inspired. I'm not sure. Okay.
Any more questions from the online audience, perhaps?
No, I know that definitely he, I mean, in his former Southampton group, there was a magnet and there was a postdoc doing magnetic field experiments for kind of condensate and ring geometry and condensates.
Yes, but now, unfortunately, Pavlos is no more in Southampton.
Yeah, I know, but I think he told that he was going to do magnetic field in Skaltech as well. Or maybe already does.
We can do it also in Westlake, potentially. There is a magnetic resonance. Dear Andrey, regarding this, your last statement that the most interesting result is when you have switch from the pseudo-diamagnetic shift behavior to again the linear constant chemical potential. Is it because in this region the topological phase is no more function of magnetic field?
Topological phase is no more than function of, but okay, obvious answer yes, because we see there is no dependence. Okay, I mean, without preparation, I can answer yes.
Yeah, so because this diamagnetic shift, so-called, it is because of this dependence that was analytically predicted in 2009 by Van Schillig. But then this region is special because for some reason this is suppressed. This dependence that disappears.
Probably the answer I am not sure, but the answer can be in the demonstration of dependence of SZ. I mean, it's tricky connected with Zeeman and different couplings. If it's interesting that only in this phase, only in this case, not only term which effectively introduced in the system the in-plane magnetic field, but also this coupling also, as I told at the beginning of the presentation, plays a crucial role. And combination of all of these factors lead to the absence of dependence of magnetic of chemical potential magnetic field. It's some kind of combination of all factors.
It would be good to have some simple intuition on that, because that's really something that is not straightforward from the very beginning.
Okay, we will work on it.
This part is really something not new, I think. Okay, Anton?
So in all these calculations, you were searching for the ground state, right?
Yes, only ground state.
So implicitly, the thermal equilibrium is assumed.
Yes.
Was it experimentally shown, the original proposal, I mean, for the Spin-Meissner effect, in the equilibrium conditions? Because so far, all the experimental data, it was kind of reproducible with the non-equilibrium, non-Hermitian model. So,
but I mean, in this model, it's already taken into account as a starting point that we have, yes, we have balance between pump and decay. Yeah, okay.
The question is about experiment.
Yes, I can answer probably. So in the experiment, you need non-resonant pumping to claim that you are close to thermal equilibrium. If you pump resonantly, this is not the case. Now, the tricky thing with non-resonant pumping is the reservoir that you necessarily create. And in all experimental work that I know, a reservoir was playing role. You know, reservoir creates potential, but also in the presence of magnetic field, the reservoir gets a little bit polarized. And this effect, if you can completely suppress polarization of reservoir somehow, then you would probably come to the ideal Spin-Meissner effect. But in all experiments that I know, the reservoir was slightly polarized, and this created supplementary terms, so affected the polarization of the condensate. So Zeeman splitting was suppressed, but this SZ, its dependence on magnetic field, was not as linear as predicted, and also there was some linear polarization appearing in the experiments. And to reproduce it in detail in theory, we had to take into account the polarization of the reservoir.
Okay.
Good. Okay, if no more comments or questions, so let us thank the speaker again.
Thank you.
So tomorrow students will come, so you have this beautiful opportunity to attract the world best students